So let's see the examples. Let's consider the C code. Index equals to 15, int y equals to 18, int z equals to 19, and int sum, and sum equals to x minus y plus z, and print f percent %d sum, and there we end. I'm not uh, doing any void main or int main and anything like that. I'm just giving you the inside code. It's for printing and everything else. So sink your head into this program first, small program. Now, obviously, as I've written here, that in a typical assembly language program, which would be exactly like a machine language code, except for the English like command, it would look as follows. First of all, let me give you the scheme, because what I've used as an assembly language is a very generic type of assembly language, and I would definitely ask you after this class that I ask you to look up 8085 assembly language. I would definitely ask you to look up the 8085 assembly language and try this in your simulator. So the scheme is add 15 to any memory, say location 1, add 18 to any memory location 2, add 19 to any memory location 2. These are all absolute values that we are adding. Immediate values, they're called immediate values. So you're adding these immediate values, and why they're called immediate values? Immediate values means you can take that literally. So normally what happens is we in other values, for example, we refer to a register or a memory address. So when you refer to a register or a memory address, it has to look up the register and the memory address for the content. But here it is taking the value itself. So immediately it can take that value. So this is the immediate value. So add immediate. So add 15 to any memory location 1, add 18 to location 2, add 19 to location 3. And we obviously, for the moment, we're not going to do anything about int sum because we don't have to declare anything. See, you can see we don't even have to declare that it is an integer. We don't do that because at the hardware level, it's all the same. So, and we are directly dealing with hardware at the moment. But we are not doing that. I mean, the assembler will. But anyways, so this is the idea that we are trying to make the computer work. And to it, it's just a value. So the we are just loading the absolute value is 15, 18, and 19 to memory. Okay, so these are the values that we're going to be using. And the fourth step in the scheme is load the three values one by one into the available CPU registers, that is the onboard memory. Why? This will make the operations smaller than directly dealing with main memory and also much faster. It's an important point here, you see. See, let me just draw you the scheme. Let us say, look at the basic architecture sequence. The control unit, the arithmetic logic unit, with the registers, interfaced with a data bus and an address bus, and other control lines, data, is interfaced with the main memory. Main memory is a large part of memory. Now, imagine if you have to directly deal with memory, what you'll have to do, you have to bring it in, bring the other one in. Access takes a time. You have to address it, get the data, work with it, address it, get the data, work with it. Then whatever happens, you have to go and do that. So obviously it takes time. Rather than what you do is you take the things from main memory, and if the registers are available, see, CPU registers are very expensive. They're built with the CPU, so there are not many available. Main memory, you can have GBs and GBs of it. This phone that I'm using, It has got 4 GB main memory. And I guess if I tell you that this has got 4 GB main memory, many of you will actually laugh at me. Many of your phones may have even 8. I don't know. If it's a good phone like Samsung or Vivo latest versions, they'll probably contain much more RAM than I have got. But it's got 4 GB main memory. You don't expect that in a register. Not exactly. I mean, you don't expect that with the registers, not exactly. Because you see, the registers are very fast, very expensive memory, they're very powerful memory, they hold intermediate data, okay, and they contain the data in there. So the main memory is much slower and it contains various addresses. The CPU, on the other hand, for example, in case of 8085, the CPU registers are the A is for the accumulator. You can't So this accumulator, and then the other data registers are B, C, which are a pair, D, E, which are a pair, and there is a most I keep on forgetting W and a Z register, I think, which are also a pair, and the instruction register and the program counter is there. Program counter, okay, program counter, and this program counter, it holds the address of the next instruction that is coming in, or the next data that is coming in, okay. And then you have the instruction register, okay, and such as these are the main ones. Maybe some other registers as well. These are the main registers there, okay. So these are all 8-bit registers, but if you are dealing with a 16-bit sequence, then you can take the register pairs together. And these, on the other hand, are because in 8085 we have 16-bit addressing, but we have 8-bit data word, 8-bit data word. So as a result, program counter, which holds obviously the address of the next data or instruction register. Okay, so this is definitely 16-bit. And if the instruction register brings in a 2-byte instruction, then it will contain 2 bytes. Otherwise, it's just 1 byte. And these rest are all 1 byte each, except that when you're taking them as pairs, they are 16-bit. So you can use, for example, if you want to use a register for holding a memory address, that will obviously be 16-bit, so you can use the pair. Apart from these, there is a flag register. These are the special registers. Special. Among the special registers, there's a flag register, which is obviously 8-bit, one word. It contains a flag that shows whether it's a zero, okay, whether it's a carry, okay, whether it's and the and the sign bit, these are all there in the same register. It shows whether the last calculation produced a zero, or if it was an addition or something, if there was a carry there, and also the sign which means that whether the actual value is in negative or positive. If it's unsigned, then that doesn't come into play. So these are all a part of the flag register. So like these are the main registers in the programming model on the instruction set architecture of the 8085. Similarly is the case with everything. Now you see, if you bring in data in the B, C, D, E, like these registers, and you use them so faster because it's already in the CPU, so you're using them. On the other hand, memory access means address bring. But you just maybe you just if you just load the for example, if you just load the 3 data that you need here, these X, Y, and Z, if you load them one after the other, then just by addressing the first one, and if you know that this is 2 bytes, then like we do in C, for example, if you load the first one, the next one will be +2, then will be +2, etc., etc. So we don't always have to mention a particular address, we just have to calculate and bring it just by knowing the first one. Like it happens in case of an array, for example, if you, when you are doing arrays, you're doing the same thing. You know the base address of the array, that is the element 0, and then from then on you can just calculate the rest of it, okay, just by incrementing pointer arithmetic. Same thing can be done here. So it's faster. So you bring it all in the registers, and after you bring it all in the registers, you just work with them. It's so much faster, so much faster, and you know it avoids having to stall the CPU for bringing in the data. It's called CPU idling time. You can avoid that. So, but if it is not so, you have to bring it in so that it becomes much faster. If you are unable to find a register, then obviously you can use memory direct. You have to use memory directly if the registers are all occupied with something else. Uh, then definitely okay. Oh, there is another register that I forgot to mention. That's a stack pointer. Okay. The stack pointer is used for holding uh, addresses for, well, it's basically a stack. It's basically the function stack mostly. Addresses for the function locations inside memory. Okay, so we'll come to the stack register and what we do later on, but it's there, and it's also the stack register also contains. It's also a memory register, so it has to be the same length as the length of an address. In this case, it will be 16-bit. Now, this is the case. So you bring it in whenever you can. Now, then, so let us say that we load the program and then we use it. Okay, so we load it in registers B, C, and D. Let's say now A is generally the accumulator, and in 8085, for example, if you look up 8085, once again, this is not 8085. This is just general. But generally, A is the accumulator. In any sort of processor sequence, A is generally the accumulator. Now, so let us say that we have built it in B, C, and D. Now, what were the operations? The operations were this: x minus y plus z. And it's bracketed, so it's very certain. You have to do x minus y first, and then you have to do z. You have to add z. So, as such, what we do here, this is what we do. As you can see, we issue the mnemonic codes sub B and C, subtract C from B basically, and the result is stored in the accumulator. Add A and D. So we add A with D. What is A? A is the accumulator. What does it contain? B minus C. So X minus Y, that is. And then add D plus Z. D contains Z. So plus Z. Now, so let us assume that we want to store the result in say location 4. So we use issue something like this: store A in location 4 in mnemonic code. This is not assembly language, but these are assembly language constructs which I'm using just to make you understand. I'm writing it like this: store A in location 4. And so you see, when you do that, store A in location 4, you are copying the accumulator register into the memory location 4. Or otherwise, what will happen is any other further work will actually wipe out this value because it will overwrite. It will just simply overwrite. So what will happen? You won't be able to store anything. You won't be able to know what the exact what you won't be able to tell what exactly was the result, so that you won't be able to use it once you do not store it and you use one more operation. Then you can't get back the result. This is overwritten. Now, what will happen once the stored is in location 4? It is secure into location 4. So it's securely in there. What do you want to do? You want to print it out. So once again, this comes in. Now the CPU is obviously connected with several peripheral devices, including the I/O controller. It is the job of the I/O controller to buffer the messages that come in, that is the data that come in, and it is print. So it comes from the memory again, let's say location 4, into the control unit, goes straight into the input output controller. The input output controller will now deal with displaying it. It will connect to the monitor and display in the proper format that is necessary. So this is how it works. So all these operations are thus performed automatically, atomically. Okay, fetching instructions, decoding it, activating the relevant circuit, putting through the data, storing the result, etc. So this is all done by the internal clock of the computer. That is the coordination of operations. So that is why it's very important. And when we were talking about clocks, I told you about the beats that are given to people who are marching past, so that they can coordinate their legs, okay, hands, etc. So the same thing here. Now this one, obviously, as I said before, that of course in case of the onboard registers are available, if all are occupied, all are partly occupied, then the instruction architecture of the computer allows directly dealing with the memory locations in memory. Which just means to say that in case that, as I just said, the registers are all full, you can directly work with it. But it becomes very slow, direct to work with the main memory. Okay. So how does it then work? Then assembly program and then assembler. See, the work of the assembler is very simple. Assembly program mimics exactly the machine instruction, but in English-like formats, in mnemonics, we call it. So in case of a compiler, a C compiler or something, we'll have to work a lot. In case of assembler, what it'll do, it will just look up the code that you have given, look up the opcode and replace the code with the opcode. That's it. So you have an instruction sequence. So assembly program, it's acted upon by an assembler, and you have got the assembled digital code. For example, assembly program that once it's almost like 8085, not exactly. LDI, load immediate. I'm using an address OXFF00. So I'm using addresses one after the other to keep it simple, and so that we can reach the addresses by just incrementing. So load immediate OXFF0015. Load immediate OXFF02 18. Load immediate OXFF04 19. See the difference of 2 bytes. This is a byte addressable machine, let's say. Now, then we will load the values into the register. So load OXFF00 in B, load FF00 FF02 in C, and load OXFF04 in D. Now we have that in BCD. So add B and C. The result will automatically be in accumulator A. Add A with D, sorry, there is something wrong here actually. I beg your pardon. We should have been subtraction here. According to the scheme that we are looking at, it should be a subtraction here. Sorry, my bad. So it can be addition, can be subtraction according to your scheme. If you follow the scheme, that we, if you don't follow the scheme, add would be fine. But since we are following the scheme that we just saw, uh, talked about a few moments back, so it'll be sub BC. Then the result will obviously be in A, and then add A with D. Okay, the result once again is in A. Now I store in OXFF06 the value of A. Whatever is in the accumulator, it goes and stores itself in the memory location OXFF06. That is the memory location of sum. But then we do the IO. Then we simply use this location to and take this into the IO controller. The value of x minus y plus z, which is stored in OXFF06. Now that goes into the sort of if you look at it here, that it goes into the IO controllers, and from where it is. So basically here, after we store it, we'll just issue the command to, okay, take the value of OXFF06, which is here, into the IO controller. Once again, you'll have to go through the CU. Now here also you could do you could IO with A also. That is to say that if you are doing it immediately after you store it in OXFF06, then you can just use the accumulator register for the IO, and that would be easier for you. Obviously, as I just mentioned, as we just discussed, it will be easy for you to deal with the register and with the memory address. Simple. On the other hand, that if you also have some more operations after this, then accumulator will no longer contain the value of OXF06, the value that is in OFF06, obviously, because it will be overwritten by the most recent operation. So in that case, if you are printing it afterwards, you have to go for this. So store OFF, print that OXFF06. OX is hexadecimal, as you can imagine. So print the contents of OXFF06. You have to issue the IO command there.